Hello to everyone, and thank you very much for your interest in my presentation. So this time I am going to present this work entitled Bioethanol Production with Carbon Capture and Storage, Potential as Carbon Negative Biofuel and Other Environmental Implications. So to begin with the presentation, let me first start with the motivation, where we are and where we go. So our planet, the Earth, is getting hotter and hotter due to climate change. As we can observe in this figure, the cumulative carbon emissions continue to increase in the atmosphere, and in consequence, the global temperature, the global warming is rising proportionality to these emissions. In order to reverse the situation, in 2015, the Paris Agreement was adopted, which in essence is the first global climate deal to fight against climate change, where almost all the nations committed to keep the temperature increase below 2 degrees Celsius and even pursue more ambitious efforts to keep the temperature increase below 1.5 degrees Celsius. In this context, also scientists have defined the so-called carbon budget, which in essence is the remaining CO2 emissions which could be emitted to the atmosphere in order to meet the climate goals. And despite there are many different estimates, almost all agree that there are less than 10 years at current emissions levels to meet our climate goals, which makes this situation very alarming. So the question is how to limit climate change below 1.5 degrees Celsius. And as we can observe in this figure, most of the climate change mitigation scenarios aligned with the climate goals depend on removing CO2 from the atmosphere. As we can observe, almost all the scenarios reach carbon neutrality by mid-century, and after mid-century, net negative emission balance should be delivered in order to meet the goals. If we focus on these 4 illustrative pathways highlighted in the IPCC special report on global warming, we can see that even for this P1 scenario, which is the base case scenario, some carbon dioxide removal should be delivered by using afforestation, reforestation, and agricultural measures, while for the other remaining 3 scenarios, we can see that beside these agroforestry measures, also carbon dioxide removal should be provided by bioenergy with carbon capture and storage, which is this yellow shade here, in order to compensate ongoing and past emissions, but also to compensate emissions from hard-to-abate sectors such as agriculture or aviation. Essentially, the further the delay on the mitigation actions, the more the reliance on carbon dioxide removal. So it is clear that in order to meet our climate goals, there is an urgent need to take rapid conventional mitigation measures, such as improvement in energy efficiency, of deployment of renewable energy technologies, but also we are going to need what is called here unconventional mitigation, carbon dioxide removal. Carbon dioxide removal consists of a set of technologies and practices which are able to or capable to deliver a net negative emission balance with respect to the atmosphere. The portfolio's carbon dioxide removal options available today include some natural-based solutions, such as afforestation or reforestation, the use of biochar, or some agricultural practices in order to improve soil carbon sequestration. But also, there are some approaches, technological approaches, which are here called engineered solutions, such as, for example, improvement of enhanced weathering, which consists of improving minerals, the sequestration of CO2 into minerals, but also, for example, here we can find direct air capture, which in essence consists of a technology which is able to capture CO2 directly from the air using chemical reactions. And finally, we find these combined approaches which use biological resources into technology approaches. And here we find this bioenergy with carbon capture and storage, BECCS, which in essence use biomass resources to produce energy, and the CO2 release is captured and sequestered into materials or geological sites, ensuring the long-term storage. This BECCS is the focus on of this work. And for those who are not familiar with this bioenergy with carbon capture and storage, BECCS in essence is the combination of two technologies, which are bioenergy and carbon capture and storage. Bioenergy consists of the use of energy of biomass resources such as energy crops, residues from forestry activities or agriculture or municipal solid waste in order to produce power, heating, or biofuels using different conversion processes such as combustion, fermentation, and gasification. The benefit of bioenergy compared with the use of fossil fuels is that it holds the potential to be carbon neutral, since during the biomass growth, some CO2 is captured, is uptaken via photosynthesis, and this could compensate all the direct and indirect emissions during the life cycle of the BECCS supply chains. And on the other hand, carbon capture and storage is a completely different technology, which in essence avoid the release of this CO2 at the plants, at the power plants or conversion plants or biorefinery, which is captured using chemical reactions and stored permanently into geological sites. And the beauty of this BECCS, of this combination, is that it holds the potential, it's capable to deliver a net negative emission balance, that is a carbon negative balance. So this concept has been received a lot of attention as applied to power and heating. However, its application to biofuels remains largely unexplored. And therefore, to fill this gap in this work, we focus on the application of the best concept to produce biofuels. And in particular, we aim to address these two questions. The first one is, would BECCS applied to biofuels able to deliver negative emissions? And the second one is that, is there any undesired environmental effects of BECCS as applied to biofuels? So in order to put some light on these two questions, we are going to use two methodologies here, which are life cycle assessment and simulations tools. For those who are not familiar with life cycle assessment methodologies, in essence, it allows quantifying all impacts and burdens of products and processes along the entire life cycle. And if you are not familiar with life cycle assessment, an LCA study comprises 4 consecutive steps, which are, the first one is the definition of the goal and scope of the study. Then in the second phase, which is the inventory analysis, all inputs and outputs of the processes are quantified, which are emissions to air, water, and soil, or resource use such as land, water, fossil, or metals. Then in the third phase, which is the life cycle impact assessment, the elementary flows are converted into environmental impacts using characterization factors and damage factors. For example, environmental impacts referring to climate change, ozone depletion, land use impacts, ecotoxicity, which refers to 3 areas of protection, which are human health, ecosystems, qualities, and resources. And finally, in the fourth step, all this information is provided to decision and policy makers, which interpret and provide some recommendation in order to improve the environmental performance of the systems. So here we are going to rely on the use of the EcoInvent database, which is a well-known database. Also, we use the CIMAPROF software to assess the EcoInvent database and the GRID database. And the second methodology used here is simulation. In essence, simulations tools allows to modeling the process under study in order to get the elementary flows which are used in this inventory analysis phase. And here in particular, we use a simulation software called Aspen Plus to model our process under our process of interest. So let me now explain very quickly the case study. The case study assessed here in this work consists of a biorefinery coupled with carbon capture and storage technologies for bioethanol production, which use woody residues from forestry activities, from sawmills. In particular, we follow a well-to-wheel approach, that is from the raw material acquisition to the use of the biofuel in the vehicle. As a functional unit for comparison purposes, we consider 1 kilometer travel in the vehicle. And in order to provide meaningful results, here we consider different scenarios, considering different bioethanol gasoline blends, as well as modifying the heating resource used for meeting the heating needs of the biorefinery and the carbon capture and storage units. We consider a fossil fuel representative, which is natural gas, but also a biomass based heating, considering sugarcane bagasse, a residue from agricultural activities. So let me now quickly explain the boundaries of the system studies, which is divided in these 5 subsystems. The first one consists of the feedstock, which includes the forestry activities, including impact regarding the soil preparation, but also some impacts in the sawmill. And here the wood chips are transported via lorry to the biorefinery. And first, the wood chips are digested in order to separate the lignin and the furfural from the sugars. These sugars are further processed. This is the fraction of interest here, are further processed in order to separate the acetic acid. And the sugars are sent to this fermentation unit, which with the help of microorganisms, the bioethanol is produced and sent and blended with gasoline for its use in the vehicle. From this fermentation unit, almost pure CO2 is released and captured and sent to this third unit, which is the capture and CO2 capture and compression. And also from these cogeneration units, which provide the heating requirements for the biorefinery and the CCS unit, the CO2 is also captured and sent to the unit, where the CO2 is captured using a monoethanolamine solvent. After the CO2 is captured, the MEA solvent is dissolved in this stripper unit, and the CO2 coming out this column at the top of this column is finally sent to the compression stage and finally transported via pipeline to geological sites, which ensure the long-term storage of the CO2. So let me now explain briefly the main results of our study, and in particular, I am going to start with the carbon footprint assessment, which is summarizing this figure, which in particular shows the carbon footprint as a function of the carbon intensity of the electricity used in the biorefinery and in the CCS unit. And as we can observe, there are several scenarios that improve the carbon footprint compared to the conventional gasoline, which is here depicted with this blue line. We can see that there is only one scenario which consists of this ethanol, which consists of a blend considering 85% of ethanol and 50% of gasoline. Only this one is able to deliver a negative emission balance, considering carbon intensity of the electricity below 0.9 kilograms of CO2 per kilowatt hour, which almost happen in all the countries in Europe, but not in Poland. And we can see that, for example, considering the carbon intensity, the average carbon intensity in the European Union, almost 3 kilograms of CO2 equivalent per 100 kilometer travel would be delivered. And for example, considering a lower carbon intensive electricity mix such as the one in Europe, which is based almost on nuclear power, almost 5% kilogram CO2 equivalent would be delivered per 100 kilometers travel. If we want to put this result into context, considering an average traveling kilometers traveled in a car of 14,000 kilometers per year, using this blend, almost 400 kilograms of CO2 would be delivered per year, which corresponds of around 40% of the per capita emissions in Spain, which is a quite significant amount because we need to consider also the avoided emissions due to the replacement of the CO2 produced by the gasoline, which is replaced by this bioethanol fuel. Uh, Now, let me show you the breakdown of the carbon footprint, which is a very interesting analysis in order to identify the hotspots, that is where the places where the main emissions came from and where the effort should be directed in order to improve the carbon footprint performance of the biofuels. So the results of the breakdown are illustrated in this waterfall plot. Here we can see that the negative emissions are coming from the first phase, which is the biomass growth due to the CO2 capture during the biomass growth via photosynthesis. We can also see that the highest positive emission came from the direct combustion. There is little to do here in order to improve the carbon footprint. But also we can see that a significant amount of the positive emission is coming from both the biorefinery and the CCS unit, and in particular from the heating needs. And in this regard, this information could be very powerful for the decision makers and policy makers in order to reduce or to improve this carbon footprint by, for example, considering another heating resources in order to be more environmentally friendly. And finally, there is well known that moving towards biofuels could lead to collateral damage in other environmental categories, such as, for example, damage to biodiversity. And here we assess the risk of burden shifting. And this is illustrated in this figure, which in essence compare two scenarios with the business as usual, which is the gasoline. And as we can observe in the figure, we consider a set of environmental categories which are taken from using the recipe methodology, LCA methodology, which is well known and its use is widespread. And for example, include ozone depletion, but also terrestrial acidification, freshwater eutrophication, land use impact, or water consumption impact. We can see that burden shifting takes place in almost all the environmental categories, despite delivering a negative emission balance in the case of the E85 blend. We can see that this burden shifting is particularly critical in eutrophication, freshwater eutrophication and marine eutrophication, but also in land use and water consumption. And this is because sugarcane bagasse is used as a heating resource. And therefore, due to the agricultural phase, due to the use of fertilizers, some eutrophication impacts arise, but also due to you need land to cultivate the sugarcane. Also, this land use impacts became very relevant, and also since the sugarcane requires some irrigation, there are a significant burden shifting to this water consumption category. And with this, I would like to highlight some final remarks. So as conclusions, here we have investigated the best concept as applied to biorefinery coupled with carbon capture and storage that uses woody residues in order to produce bioethanol. We showed that only blends with higher bioethanol contents would be able to deliver negative emissions. We have also seen that it's very important to move towards the use of low carbon energy resources, both for electricity and heat, in order to improve the carbon footprint performance of the biofuels. We also have seen that it is very important to widen the scope of the future policies, because nowadays almost all climate policies focused only on climate change, and it can lead to significant to important collateral damage to other environmental categories, such as damage to biodiversity or to ecosystems or water consumption impact. And finally, as a final conclusion, this BECCS concept, as applies to biorefineries, offers a great opportunities in order to provide negative emission balance from the transportation sector, which, as we seen in as I explained in the motivation of this work, delivering negative emission could be crucial in order to meet our climate goals. So that brings me to the end of my presentation. Thank you very much for your interest in my work. If you have any questions, you can reach me at any time in this email address. And also here, I would like to take the opportunity to say thank you to the co-authors of this work, because this was done in collaboration with researchers from the Universidad of Santiago de Compostela. And also, I would like to prompt you, if you are interested on this work, this has been recently published in Applied Energy, and in the paper you can find more meaningful, more results, and a very detailed discussion of the potential of biofuels to deliver negative emissions. So thank you very much. That's all from my side.